Okay, so good afternoon, good morning, everyone, and welcome to Starknet All Core Devs call number 43. So, before we begin, a quick housekeeping item. We'll be recording this session for those who could not join us live today. And please keep yourself muted when you are not speaking to minimize the background noise. And I also want to remind everyone that we are at a 12 p.m. UTC time slot, which will remain effective till end of March. And welcome back, everyone, from the holidays. This is our first call for 2026, and it's a special one. We'll be running for about 45 minutes today, just in case, instead of the usual 30 minutes, because we have a special presentation from Andrew at Starkware on Propeller, which is a new P2P messaging protocol. We have five main agenda items to cover today, plus the Propeller presentation. And I would like to keep us on schedule to respect everyone's time. So let's get started. So our first agenda item is the 2026 roadmap and decentralized validation plans. So Ethan, in our last call on December 18th, you mentioned you were in the middle of evaluating what you will be doing for the next year and creating a 3 to 6 month detailed roadmap. So you also said you believe that you would have published the roadmap by this call. So let's start with that. So if you can share the details, like is the roadmap ready to share with public, and like how are things going on?
Yeah, we have a rough outline on it. I don't have to share here a presentation on the roadmap, but I can share. I'm just letting other people join the meeting. I can share that outline that we're working towards. So the idea is to have by end of Q3 a decentralized validation setup, which basically means that although that all blocks that are being introduced to the network will be voted by a decentralized set of validators. The idea, and we're going to call this version 0.15. So this is what we're working towards in the next 0.14.x versions that we'll have coming out until we reach that milestone. We're shaping up the exact technicalities of what we'd like to see in those 14.x versions so that we can best prepare ourselves and the community and take small steps towards this decentralized validation goal. Originally, with decentralized validation, we'll introduce it in an Apollo setup, meaning that we'll have Apollo proposers that are proposing blocks and Apollo validators that are run by the community validating these blocks. So now, as a part of that process, the things that we're working on are setting up the staking rewards in such a way where attestations are based off of participation in consensus. That's one thing. Another thing is packaging up Apollo so someone can run the validator side of a node outside of the current setup, meaning you wouldn't necessarily need to have a gateway or a mempool, but you do need to have a setup where you can read transactions that are coming through the consensus peer-to-peer network and validate them so that we can create these blocks. So these are all the milestones. These are the different steps that we're working towards to reach that 0.15 flagship version of decentralized validation. Once we go there, then later on in the year, towards the end of year, we'll be working on the beginnings of decentralized proposing. I'm not going to get into technical details on that now because we have yet to discuss the specifics of what we need to do to get to that with small milestones. The reason that we're doing this in small milestones for decentralized validation is because we're learning from previous events with 0.14.0, where we did a really big upgrade very ambitious. And one of the big things that we learned from it is to kind of spread out these goals into more baby steps so that we could really incrementally, slowly, surely reach each and every milestone. So that's what we're looking at for 2026. Those are the big things. Those are the minor goals that we need to reach to get to these grander goals. So yeah, that's the roadmap update.
Okay. Uh, Thank you for the roadmap update, Ethan. And now staying with you, can you give us an update on the post-deployment network status? Like in our last call, you mentioned that there were some 502 errors that were affecting some users post-deployment, which were connected to the DNS system setup and caching. So the investigation was ongoing at that time, as far as I remember. So can you give us an update on what you found and what has been resolved?
Yeah, so we had a DNS caching work in such a way where we recommend a certain amount of time that you should cache our DNS address. We had reduced it, but as a server, you can't force the other side to adhere by your or our recommendation for how long you should cache DNS for. So these mishaps were more the likelihood of someone who was caching the DNS for longer than what we had recommended, and therefore they saw an extended period of time where they had some trouble accessing the network. Now, what we are considering doing in next upgrades to mitigate it is addressing certain workarounds where we can actually connect these networks in the back end. I don't have the specifications on how we would exactly do that, but it's in our playbook in terms of how we could take an extra step towards helping out users that might not have paid attention there.
Mhm.
Another thing I want to talk about, because we did have a reorg since the last call, so it's important to share what reasons were and why we had to go ahead and have a reorg. So what we noticed early on, I think this was last Monday morning, was that there was a disagreement between our batching service and our proving service, meaning that the transaction that we executed was not able to be proven. And this is the beauty of having a Validium setup where you actually have to prove the state diffs. And if something happens that you can't prove, then it's a red flag and you have to deal with it. But nothing's getting settled to L1 that's not legitimate. So we saw one of these incidents on last Monday morning. And we, as quickly as possible, decided that we needed to take down the network to investigate it. We ended up doing that after 507 blocks. Each block is being created within around 2 seconds. And then we started to try and debug the situation. We found that the bug was that in execution, when you execute a contract that does some sort of formation of reverting, where you're going into functions, changing values, but then reverting out and going back in, there was a very, very specific flow that the revert on one of the calls didn't cover all parameters in the function, meaning that we didn't revert on a specific field of a specific function, and that created the mismatch. This was quickly patched and deployed, and we were able to get the network running again. So that was in regards to the reorg. And in terms of an actual postmortem, I'm not sure. I cannot remember if it was already shared with the community. But if it wasn't, then we'll be sharing that once it's prepared. And if it was, then I'll try and find that and ping that in the relevant channels.
Okay. Okay. Thank you, Ethan. And now moving on, we have our presentation from Andrew. So I would like to invite Andrew to present the presentation on Propeller, which is the new P2P messaging protocol.
All right,
Yeah.
I'm excited. Can you hear me?
Yes.
All right, that's great. So I want to talk to you about propeller and block propagation. Let me know if you can see my screen or if I'm sharing.
Yes, we can see your screen.
All right, just a second. All right, okay. All right, I'm gonna start talking about block propagation. Feel free to like interrupt me if you have any questions, if something isn't clear, and we can kind of, I think we have like we're making good time, so we have time if you have questions. All right?
Okay. Okay.
All right. So block propagation. Block propagation is the act of kind of taking I seem to have a bug in my slides. All right. So taking a block that you currently want to propose as a proposer in the network and sending it to everyone else in the network. So that is what block propagation is. And it's an important thing to kind of think about. Oh, here it is. It's an important thing to think about because it dictates the theoretical maximum transactions per second that you can do on our network, or as a matter of fact, any network. This is a fundamental issue in any decentralized blockchain. And if you can't send these blocks or this data fast enough or with enough throughput, then you will never be able to kind of pass a set amount of transactions per second. Is that clear? I'm assuming someone nods. Yes. All right.
Yeah.
Yes.
Okay. So here we're gonna look at some numbers that you can kind of calculate and see that it's an actual limit that is important that we look into. And Gossip Sub, and we did a lot of benchmarks with Gossip Sub, and we also looked at what others have done around benchmarking and kind of figuring out what's the maximum throughput that Gossip Sub can reach. It's the state of it's the most used algorithm. I don't want to say state of the art because it's not exactly state of the art, but it's the most common one that is used right now. It's used by Ethereum and we use it. It's not exactly designed for high throughput by one broadcaster. And we've seen a lot of things that show that it just won't be able to hold up with the transactions per second that we're going to set for ourselves. And so we came up with an algorithm that's called Propeller, and we'll kind of explain why we did this or what happened and what it is actually. All right, so it's a new protocol that we developed. It's not something we took from anywhere else, and it's heavily inspired by other blockchains or things that they do. Specifically here, I think we looked at Solana, and we took a lot of ideas from there, but we kind of worked some stuff in that we thought was important for our specific use case. And we can talk about that. We can kind of explain the differences in the end. It uses error correction codes, so Reed-Solomons or other codes that you might be aware of that allow you to kind of fix data and when you have data loss, and we'll explain how that works in a second. And it distributes the network bandwidth amongst all the validators that are in the network.
Mm-hmm.
All right.
Okay.
And we kind of designed it for Tendermint in mind. We'll see what that means in a second. What does it mean to have Tendermint in mind when you're designing a network layer? So let's start with Tendermint. So it's a very well-known consensus protocol. I'm assuming many people in the room know what Tendermint is. It is the thing that allows us to agree, the protocol, the algorithm that allows us to agree. What is the state of the chain? What is the newest block? Are we all agreeing on it, to vote on it, and such? Now, it takes the way we're kind of looking at the design today, it's that it takes messages from Propeller. So Propeller kind of does its logic with TCP or Quick or any other transport that what we would like, and then it passes its messages on to Tendermint, just like many of the network stacks that exist out there. It's just a similar concept. And the kind of underlying assumption in Tendermint is that less than a third of the nodes that you have in the system or the blockchain are malicious or are bad in some sense. Okay?
Okay.
Now, the gossip property is a property that Tendermint assumes from its network layer. And it's written in the paper somewhere, you can look at it. And if an oversimplified version would be that if one good peer receives or publishes a message, then eventually all good peers will receive it. Okay? This means that it's called the gossip property because you're assuming that the good peers are kind of gossiping between them about the messages that are out there and are exchanging this information. And if you don't have this property, if your network protocol does not satisfy this property, you can reach certain situations that I'm going to show right now. All right. Let's start with a basic version of Propeller, and then we'll show where's the issue with this. Actually, no, I'd like to just say if you don't have the gossip property, then you would have issues where a certain validator would only agree to a certain block, and that block does not exist for everyone. And you can kind of do this attack where you lock you lock validators on certain blocks that they will never come. All right. So Propeller, so our first draft, kind of a simplified version, and I would warn you, this version does not fulfill the gossip property, and we'll see how we can kind of change it slightly so it does, all right? So the first version assumes that you have a total number of validators, in our case n, and n minus 1 is the number of validators without the proposer, and we define f to be n minus 1 divided by 3, and then floor that number to get the number you want. This is coincidentally the maximum amount of bad or faulty nodes that you would have in your system under the same assumptions as Tendermint. This specific calculation is also done in Tendermint as well to describe what is the maximum amount of bad nodes. All right, and so we start this entire conversation by assuming that everyone knows who are the other peers that are in the network. Oh, sorry. So everyone knows who are the other peers in the network, and we order them by some order. Here we can just order them by peer IDs, but we also always assume that the proposer, we give him the kind of special number 0. So the proposer is number 0, and everyone else is peer 1, peer 2, until n minus 1. And the order is known by all. This is very important. Now, the proposer takes a message that he gets, can either be a block or part of a block, depends on how we decide to do it, which adheres to the best performance characteristics that we see when we're benchmarking later. And they take this block and they divide it up to f equal shards. And there is significance here, we'll talk about it. And these shards we're going to call data shards because they come from actual data that you would not want to send on the network. You then add an additional n minus 1 minus f, so it's around 2f shards. It's either 2f or 2f plus 1 or 2f plus 3, plus 2. And you add these shards using some error correction code. In our case that we're specifically benchmarking at the moment, we're looking at Reed-Solomon error correction. And you add these shards. And the way that it works is then whenever you have any f shards, you can still reconstruct the data. So if you lose part of this, if you lose 2f shards, you can still construct the data no matter which shards you lose. All right? So that's how error correction works. Now, the proposer takes these shards, and we know there are n minus 1 shards, takes these shards and sends a shard per peer that exists in the network. So peer 1 gets shard 1, peer 2 gets shard 2, peer n minus 1 gets shard n minus 1. So everyone gets a shard. And now what they do between them is that they broadcast to each other their own shard. All right, so you're kind of distributing this effort of sending a message to a network by dividing it up into small pieces where redundancy exists between these pieces. And then you give each piece to a different person. That person is responsible for broadcasting it to everyone else. All right. From the top view, it says exactly what we're doing right now, which is first you send your shards, and then they send them to each other, and then everyone has the shards, and they are able to construct the message. The good thing of this specific approach is that no matter how big the message is, everyone is required to have the same amount of bandwidth, which is 3 times the amount of the length of the message. So if you're sending a 1 megabyte per second, okay, which is some amount of transactions, you're sending 1 megabyte per second, you would multiply that by 3, and that's the amount of throughput that each person in the network needs to have. Okay, now don't get excited, guys. This might change depending on your stake. We do have plans to kind of maybe change this. So it's not exactly like 1-to-1, you will always have 3 times the bandwidth, but it is the thing that the first draft is starting with, and we'll kind of see how this might change. All right, so the big issue with this is that it does not have the gossip property, meaning that there is a case where someone can receive a message and some good peer can receive a message and other good peers don't receive it. And the specific case that we're going to look at is when you have 2 malicious peers and they are specifically targeting node 5 in this image, okay? And you can see that the first bad peer is the proposer, and it sends node 5 its shard, and it sends another node its shard, and it sends its other bad peer its shard. And this peer specifically targets the 5th peer, and it doesn't give it the shard, okay, that it's supposed to have. Oh, now that this image might have a mistake in it, I think.
Yeah,
I think we're targeting 2, right? In this case, yeah, they're targeting 2. Yeah, I think they're targeting 2. So if you look at the second node here, you know that it received its own shard. From this drawing, you see that it received a second shard from this bad node, and also received a third shard from this bad node. It is now able to build the message, and will build it and receive it, while we have the 5th node here, or maybe other nodes in the network, that did not receive the message. So what would happen later on in Tendermint is that node 2 would decide that this is the proposer that I'm going to accept, and it will lock on it. It's called like a locking attack. It will just stay on it. And if you get 2 nodes, the good nodes, to lock on different values, you have a kind of thing where you kind of stop the progression of Tendermint. All right. So yeah, one good peer receives the message, but not all good peers received it. I might have a bug in my slides here. All right, propeller. We fix this by first doing the first step, which is distinguishing between a message being built. That means that we have it in the propeller layer, and a message being received where that message moves on from the propeller layer to the Tendermint layer. And when Tendermint assumes the gossip property, we're talking about receiving here. Okay, so if one node receives, one good node receives, all good nodes should receive. But with regards to building, there is no such constraint because Tendermint doesn't even know that a message has been received. Okay. All right. Now, the idea that we have here is to say when F shards arrive, I can build a message. And this is true because we started with F data shards. So any number of shards that is data shards or more, we can start building, we can build the message. And we add an extra constraint that might seem like it's foreign now, where when we have 2 F shards, so twice the number of build shards, we can receive this message. Okay, we know that we've already built it because we've already reached the F cutoff that we build in. So we would have the message and we would wait for 2 F shards and then receive it. And I will explain why 2F is special. Because if I'm a good peer and I just received 2 F shards, I know that I got each shard from a different peer. And if I receive 2 F shards, that means there's at most F shards that are faulty, and thus at least F good shards that I got from good peers. All right? So now that I have F good peers, and I know these peers have their shards, I know that they would broadcast their shards to everyone because they're good peers. They're behaving in the way that Propeller expects. And now that everyone has F shards, because these good peers would send it to everyone, everyone can build the message. All right, so that's kind of the big kind of realization why 2F matters, because when you know you have 2F, you know that everyone can build the message. Now, we add an extra constraint where we say, okay, not only are you expected to send the shard when the proposer sends you your shard, you're also expected to send your own shard when you are able to deduce it yourself. So if you look at what the proposer would do, they would take the message and divide it and do these kind of math algorithms on the message and devise the shards for each person. Once you have the message yourself, you can do the same thing. And you can come up with your own shard. Okay? And so you take responsibility over this act. And once you can build your shard and you haven't already sent it or broadcasted it to everyone, you calculate it and you send it to everyone. That's it. These are all, the only two changes that you need to the previous algorithm. And what you get is a very nice feature, where before we saw that if a good peer receives a message, that means they got 2F shards, which we deduced that means that everyone can build the message. And now that we know that everyone can build the message, we know that good peers would build the message and find out their own shards, and then broadcast their shards to everyone, forcing the network to have forcing everyone in the network to have at least 2F shards, or forcing everyone in the network to receive or to be able to receive the message. Okay, so once we know I have 2F, I have this kind of very nice property that I know that everyone in the network has the message and we can give it to the Tendermint layer without having to worry about it not having the gossip property. All right. So in a happy flow, you would send your shard to messages. And did I say build? I don't think I should. This build right here does not mean anything. It's kind of a bug, I think. So you receive your own message. Oh yeah. In this case, I think it does say build because here we have four nodes. So F would be 1. So you can already build with your first shard. And as a matter of fact, this green shard right here would be just the message itself because it's error correction with one data shard. And then each node would broadcast its shard to everyone else, and then everyone would receive because they'd receive more than 2 shards, which is 3 shards in this case. All right. If I have a faulty non-proposer, then I would send them the message, and the worst they can do here is just not send it to anyone. And that would still not stop the algorithm because they send it to each other, and they're only waiting for 2F shards, and they would still receive. If I have a faulty proposer, they can kind of try to do a better attack where they send it partially to see how they can kind of hurt the network. But if they send it to less than F shards, nothing happens because no one can build and it doesn't go anywhere. And if they send it to exactly F shards or more, these F shards would send their message to everyone else, and then everyone could build, and then everyone could receive under the same logic that we followed so far. All right. And the attack that we had before is no longer possible because, I think this attack is a bit different. Anyways, these slides were kind of Frankenstein together from other slides, but the attack that we had before is also no longer possible just because you would not receive, you would just build that specific scenario. All right, and in terms of performance, we've worked on this for a few months now and we've kind of optimized it and made it work exactly like you would expect. There are certain kinks to iron out with kind of performance implementation details, but the general idea is that it's able to do extremely well when working with like 50 nodes. This is what we have right here. So 50 nodes, 10 megabytes per second, which is, let's say, a lot better than Gossip Sub. And we're kind of forcing messages or packets here to have 180 millisecond ping latency. We've looked into other constraints, and currently we've seen that we were able to kind of be extremely stable at this specific rate. We're also working towards increasing this, but it's able to kind of do very high latency, very high throughput in applications where Gossip Sub would not have any chance of doing the same. And the kind of theoretical latency advantage here does not only come from kind of the design, but if you look at it, you receive the message on average on 2 hops. So you do two jumps to the network, and everyone receives the message. This is not true in Gossip Sub, for example, where you need to like propagate the message out, and you would have just longer block times because of this. So this is basically Propeller, and I would really love it if you could, just if you have any questions, to feel free and ask them, and thank you for listening.
Thank you, Andrew. Does anyone here have any questions that they would like to ask? Mm, I don't think so. I guess
No,
everybody
I heard
understood.
something. Someone was saying something.
My bad. Do we have a code reference already? We would love to have a look at this.
I would love to share a code reference. It is on the repo. It's not on the main branch though. Some of it is that's going on the main branch, or at least one of the main branches that we have. So I think I'd ask Aitan, and maybe we can coordinate sending you like a very drafty branch, or you can wait a few weeks and we'd have it on like a more organized kind of branch.
All
You
right,
know?
all right. Yeah.
But I would really love it if you find like anything that you could see and maybe think we could do this differently. I would love any suggestion, and I really encourage it. I couldn't state it. I couldn't like understate how much I would love that.
Sure.
I also saw a question in the chat whether votes will be also in Propeller. So votes, we have like a many to many. Like there's no one proposer that sends votes. Everyone sends votes. So we think, and votes are small. So what we think we'll do is use a flood sub, which is one hop, and because it's a very small message, it's the thing. The issue with flood sub is that it's not throughput efficient, but here it doesn't really matter. So that's the plan, to use the Propeller for the block propagation itself, and for votes to use the flood sub.
I'd also like to state that we had someone outside of like a team outside of Starknet to look at it, and
Informal systems.
yeah, informal systems. That's the name. So this has been looked at in a, let's say, more formal way, theoretically, not implementation. But yeah, we're working on it, and we're thinking we're gonna publish an organized specification in the coming months.
Okay.
I have one more question, and it's more a bit technical. I know you guys are implementing this in Rust, I believe.
Yes.
And I think we would like to also do an implementation in Go as well, right? Because we have to do it in Go. It doesn't match us with doing the thing. And I was wondering if you guys had any plans of like building a spec, having a mono repo, like similar to a libp2p, right? Where you have one mono repo with spec, and then everybody applies the spec, so we can have a crate. Or you can have like a Rust implementation that we have the Go implementation. And then at the same time, it's also open for the community to implement in Morlin, which is the same Propeller.
Yeah, we're definitely going to, once we have it implemented and organized, we know exactly the small, the low level details of how it will be. We will release specs on how to like implement it yourself. So, and then it will be much more easier to implement it in other languages like Go.
Yeah, and do you plan to open it or have like a repo, or you're gonna do it in the sequencer mono repo?
So currently it's in the sequencer. It is going to sit in its own crate, so one could theoretically import it on its own.
Yeah, we might even publish it.
Yeah, we've looked at many options. There was a draft that I personally tried to publish to libp2p, and then they kindly asked me to, they told me basically that they don't just accept any protocol. I have to go through some proper channels, and we're considering these things. It's just it's really a matter of time, and we'd love to hear what your opinions on it and how important it is to you that we do a certain thing or another. It's really
just from a place like I've been developing Starknet for a while, but always outside of Rust. And the thing is, like one of the things about Starknet is sometimes it's very Rust centric and very Rust friendly, but a bit unfriendly sometimes when you try to build outside of Rust. And for example, in this case, I don't know if you guys consider it, but try to make it instead of a sequencer. I don't know how it works, right? Or at least publish the specs, because the idea is then because for Juno specifically, we cannot implement it in Rust. It doesn't work with us. It doesn't give us, and I think for the ecosystem, it's also not good to have just one single block propagation implementation.
I agree with you completely. The design decision that we took is that we built it on top of libp2p, so it should be easier than just to do it bare bones and go. I don't know if we're actually like ourselves as Starkware will work on a Go implementation, but it will be.
I don't want you guys to work on it. Like, I don't want Starware. I would like for us to work on it because it's of our interest to be super optimal and stuff. But what I want is like, because what can happen and what will happen is that you guys make updates to it, and then let's say we're maintaining the Go implementation, then we get like behind. Oh, there's a new release. We have to update now. And then if we're going to go this way, also to create, maybe not something to discuss right now, just thinking about the role around it and how fit it in an ecosystem with multiple languages and with more sequencers that only the stacker one.
Absolutely. No, this is something that, frankly, I think keeps both of us at night, and we don't know what decisions we can make here to make it even more portable. And God forbid if we need to change it in the future because of some constraints that we can't see now, how do we do that? But I think we'll figure it out. I think we'll communicate and we'll be very clear about what we intend to do, and we'll see how it is on other languages and what you guys can do, and make sure that we do these changes together in a way that works for everyone.
Okay, thank you.
Any more questions?
There was a question in the chat.
Yeah, I think we answered that. Let's see, it's the same one.
Oh, sorry.
If a node receives two F messages, how does it know which subset of F messages should be used to construct the full message? Okay, so there are some things that we haven't mentioned, but the base idea is that you're sending like a Merkle root of the message, and each shard comes with a proof that it's part of the Merkle root.
So this is actually a very good question. I'll just like stop you there. I'm absolutely impressed by who sent it. Really, it shows that you're really focused and you know exactly where to press the buttons, and you are actually pressing very good buttons. And yeah, we've thought of this. This is a very, very big issue. The solution that we came up with is that, like Shafik said, you would have a Merkle root of all the shards, and you would sign that root. The publisher would sign that root. So if you tried to kind of play around with, I'll maybe send shards that will not allow you to build the message and other shards that will allow you to build the message, everyone would be allowed to see that. And what we've done in our implementation is that once you build the message, you make sure that there was no foul play. And you know that the foul play will only be possible by the publisher because they signed the root. So it's kind of like there are many layers of security here that allow you to do this. Because if you think about it, I can't send a shard out just spontaneously. How do I prove that that's even a shard that the proposer intended? And we do this in two ways. One is that if you build the shard correctly, you would reach the exact shard that the proposer would build, and the proposer is obligated to put that shard into the Merkle tree, because otherwise, when people are validating it, they would get a false validation. They would see that there has been an issue here. So very good question, but yeah, we've thought about this. We haven't really given you the full picture here, just for succinctness, but we've thought about this.
Okay. So thank you, Andrew. That was a great overview presentation, and it's an exciting thing, to be honest. So now let us move to our client team updates. So we'll now hear from each of the client teams about their status post holidays and their Q1 priorities. So I would like to ask each team to give their updates to approximately 3-4 minutes, because we are running out of time a bit. So we'll start with Christian. So Christian, welcome back. In our last call on December 18th, Pathfinder VO.21.3 was stable with no issues. So how did things go over the holidays, and what are your plans for Q1?
Okay, so there actually were two updates since then. One update is related to last week's issue on mainnet. which required us to upgrade our blockifier dependency so that we produce the same reverted transactions as the sequencer does. And another update was made necessary by an actual bug in our HTTP2 implementation, or to be more precise, it's not an implementation we have implemented, it's a library we use. It turned out that right after Starkware has enabled HTTP response compression on mainnet, Pathfinder nodes started having issues with keeping in sync. The symptom is that our HTTP client, which is responsible for fetching data from the Starknet feeder gateway, has just stopped sending out requests. And it turns out that this is a bug in the underlying H2 crate that was fixed in the latest version, which was released late December last year, something like that. So we have released Pathfinder 0.21.5, which is our latest release, which has a fix for this HTTP issue that made Pathfinder syncing unreliable after HTTP response compression has been enabled on the feeder gateway. That's pretty much what happened since our last meeting. Other than that, we know of no issues, and we think that our latest release will work whenever HTTP response compression will be re-enabled on Starknet mainnet. As for plans for this quarter, we are primarily focused on implementing consensus, matching with the Starknet roadmap. We are concentrating on being able to provide a package using Pathfinder that you will be able to run a validator node in the distributed consensus environment. So that's pretty much our priority. In addition to that, obviously, we will be working on keeping up to date with the latest Starknet changes in the 0.14 point releases. But the primary goal is distributed validation.
Okay. Thank you, Christian. Let us now hear from the Juno team. So, Rodrigo, in our last call, we had released on time with the RPC issues fixed, and your focus was shifting towards optimization, consensus work, and some database improvements. So, what's the status on all that work after the holidays?
Yes, so our current focus for January, it's actually cutting database size. I think we're aiming around 40% cutting database size. We're now playing with it because we need to change a bit of the things, but I think by the end of January, we could have a release with which applies the migration and then cuts size of the ID considerably. After that, we also plan to focus on P2P, and at the same time, we're working for an improved try, which should come also around February, March, which is just to keep the state in a more efficient form, and that will allow for, if we want, later to apply better things such as snap things. So that's mostly it. But beyond that, we also start the quarter. This quarter goes to, of course, the centralization and getting the centralization in and optimizing all that is this pipeline which is executing stuff.
Mhm.
Yeah, and now we have to
Okay.
do a profiler as well, so I will see how that fits in, and yeah, that's mostly our things. Yeah.
Okay. Okay. Thank you, Rodrigo. And now let's hear from the Carnot team. So, Himank, in the last call, you mentioned that Madara and the orchestrator 14.1 release were planned for end of December. So did those releases go out, and how is everything performing on your end?
Yeah, thanks, Ayush. So yeah, Madara resequencer and full node 14.1 support has been completely out there. So both for Madara sequencer as well as the orchestrator, it's running perfectly well. We have been doing a lot of paddle testing there, and we've done a lot of fixes on the orchestrator to gain more confidence on it, and it's performing really well now. On the SNOS side, we have done a pre-release for 14.1. We are waiting for Dojo team to review our PRs and get it out as a release. So that's one thing on the SNOS side. Apart from that, we have been doing a lot of testing on our end, December end and January starting. That has been on the Cairo native side. It's performing really well on Madara, where we're gaining a lot of performance there. We might put out a performance report there, but yeah, that's not confirmed yet. But yeah, we're getting a good amount of testing and performance there. Apart from that, we are focusing on getting Madara full node to the tip of Starknet, Sepolia, and mainnet. It's been a while now that it's not been there, and we're gonna be like thinking of using it as a legitimate full node for that. We'll be using our SnapSync feature that we shipped last year to get it to tip as soon as possible. We could also put out a report on how much time it took for the huge amount of blocks that we have on Starknet. And majorly this year, we are focusing on keeping up to date with Starknet updates now that we're finally on sync with the latest updates. Finally, that Madara is on sync, so we would want to be up to date with all the updates out there. Yeah, that's pretty much it.
Okay. Okay. Thank you, Hema. And the next point on our agenda was consensus updates, but I don't see Jasmina present here, so we'll skip that part. And anyway, we are short of time now, so we'll move on to the section 6, which is like any other business. So does anyone have any other topics that they would like to discuss or any questions for the group? If you have anything, you can raise your hands. I guess everything is answered today. All right. So if there's nothing else, let me close the call. So thank you everyone for joining our first call of 2026 and for all the updates that you have shared. A few reminders before we close. First, a special thank you to Andrew for the propeller presentation. Really exciting to see some new infrastructure work for the network. And our next call is scheduled for Thursday, January 29th, same time. That's 2 weeks from today. Back to our regular 30-minute format. As always, the recording of today's call will be published on the YouTube channel, and the meeting notes would be shared on GitHub. So thank you all for your time and contribution. Have a great rest of your day. I'll see you in 2 weeks again.
Thank you. Cheers.
Bye, everyone.